finite element analysis. That's where the name of the business...
It's in the name.
Yeah, it's in the name, Element Engineering Australia. And it's basically the reason why I started the business. This is Daniel Birdie, the lead mechanical engineer now. Dan came and started working for us in probably about 2012.
Yeah,
a couple
12 years the other day, it was.
Yeah. I met Dan at the UWA Motorsport team. Alumni would come back and basically quiz the students on why they designed that part of the car, and you were doing simulation.
Yeah. So see, I was doing computational fluid dynamics, so aerodynamics analysis of the vehicle at the time.
And you could hold a conversation.
And I could hold a conversation. And I wasn't sleeping like one of the guys, I think was.
Someone was sleeping on a chair. Someone else was not talking to anyone, as most engineers do. Dan came across and sort of learnt the trade. At the time, we were using SolidWorks simulation as the first port of call, and then we bought a license of the Abacus CAE. We did a lot of work with that, but Dan, you were the one that basically wanted to move to ANZUS. You took a long time to convince me, but I think it's paid off in the end.
Yeah.
So what were the reasons?
I had a bit of experience with it before doing the CFD stuff. I think both you and I were probably fortunate and unfortunate at the same time enough to have gone through the time when I guess it was probably a bit more difficult. You kind of had to understand more of the fundamentals than you do now with the newer softwares that kind of just plug and play, which, you know, is where some of these dangers that we're seeing come in, just the accessibility side of it. Whereas we had to really kind of understand, it was a lot more manual inputs. Yeah,
but we still had it pretty good compared to the guys before us. Some guys before us were writing Unix shells or Python scripts or whatever it was.
Yeah, we might not have done it.
We did it well because we understood the inputs, or we took the time and effort to understand the inputs, which gives you good outputs. We
had Abacus before, which was obviously very powerful, particularly for, at the time, like rubbers and composites and all that kind of thing. It was kind of at the forefront of being able to simulate that. I think we hit a point in about 2015, 2016, I think it was, where we're like, oh, well, I'd used ANZUS before. We knew that at the unis, that was pretty much the standard that they taught, and I think it was a fast evolving software. I think we even looked at Abacus, the newer ones as well, but at the time it seemed ANZUS was a bit ahead and people were more familiar with it at the time.
And the graphical interface was faster to bring a model in from SolidWorks, bringing it in, configuring it with your correct inputs.
Yeah, the plug-in input,
one of the things we always did was we had to make a model specific to how we wanted to simulate it. So we would bring in different bodies. If it was a plated structure, like a shell model, or we'd bring in actual physical models, and then we would bring in even welds. And we would basically create the model in SolidWorks that would be input into Abacus. We would set all of those things up individually. Sometimes I remember selecting faces of welds and things like that, where a lot of the time the automatic system wouldn't work well, wouldn't match up the faces for things like that. And then you would do this iterative process where you would figure out what you think needs to be changed. You'll process the results, figure out what needs to be changed. You'd then have to go back into CAD and change the geometry, and then re-import it and do that setup process again. So I remember some of the big jobs that I did with lightweight, high-performance truck trays, that you would run the simulation overnight. You would then come in the morning and you'd be excited to see what the results are. Have a quick look at the results, understand where the hotspots are, then discuss with the client, okay, this is the outcomes that we basically had, come up with an idea of what you're going to change in the geometry to basically optimize the next iteration. You do the rest of the work during the day to change the design, re-import everything, and then you hit run again and you go for a coffee or whatever, or dinner, come back, make sure the thing's gotten through the input step, and then let it run for the night. And then you do that over and over and over again. You can get one iteration, 1, 2, 3 iterations a day. Some of the big models was only 1 iteration a day. But it's different now. There was parametric simulation modeling back then, but it was harder to set up, and probably didn't have the computing power to be able to run 2, 3, 4 simulations overnight. Like, what are you doing now? You're doing...
Yeah, now we can queue up for 7, 8, like I think a factor of 10, 15 or more, even faster. But then obviously the interface as well allows us to modify the geometry within the actual, pretty much in the software, it's linked. There's no manual re-importing of solids back into the software and then having to set it up again. It's smart enough that for the most part, if your contacts are not significantly different, you can just increase thicknesses where you need or whatever.
Yeah, and you're also doing some of the changes not in the CAD software, you're doing it in the sort of middleman, the space client, or whatever it's called now.
Yeah, so now it's Discovery, which to be honest,
Discovery.
I actually haven't even used it.
It's a pretty powerful package.
But that's like an upgrade on even, space claims, so they say. It's linked directly to the mechanical solver, so I can essentially, there's a direct link between the geometry that you see in here and that editing software, and allows you to just change things on the fly. You can set things up parametrically really easily. So with your geometry interface, you can select a dimension that you want to be parametric if it's a thickness or a size of a weld. I can go, okay, cool, I want to hit the parametric button on that. I want to run, you go back to your table, which is in Ansys Workbench, and you say, okay, I want to run 5. You hit run, it will just run all 5, one after the other, straight after. So you can come back next morning, pull the result, which is also 20
simulations in a matrix of different changes.
Exactly. So that process is just a lot more seamless now. I think that's where it's really evolved as opposed to before, and I think just the user input now compared to before is hugely reduced. Obviously you've got to be a bit more careful, I think, and make sure you check things, which I think a lot of people don't. We've got the experience of the things that could go wrong when you're doing things manually, to be able to pick those things out. So I know my involvement now is obviously a lot more. I don't really set up the simulations. The team's doing a really good job of being able to take that or learn from me and each other. I jump in when there's more issues because I can debug pretty quickly. But having said that, it all still comes down to your inputs. So no matter how good the software is, if you don't understand what you're doing, what you're trying to simulate, or what the conditions are, it's really meaningless.
So one of the big things that I remember that I discovered kind of the hard way on the job was sort of simulating global structures and looking for local hotspots. So I've seen people break models up into very small things, and you sort of have an input on that small part, and then that provides an input on another model and things like that. But we've kind of found over the years that a lot of the time you've got to model a lot more of the structure because it's a global system, especially welded steel structures, where one part is under stress, and it's the flex of the whole system that then basically imparts a point load on one specific thing. So, when I was doing a lightweight truck tray called the flex floor back in the day, we had a spider structure which then had a suspended floor, and we had these beams that were coming down the spider structure and up the front wall. One of our data loggers, which had a G-force sensor, we could basically understand what forces that this thing was undergo. It would have 200 tons of ore in the back of this truck. And the biggest loads that we found from the data log was when the guys were braking and cornering with 200 tons of force in this truck tray. It's pretty crazy forces. And you're talking 0.25 Gs or something like that. That's probably equivalent to a reasonable corner in a car on the road, with a 200 ton truck. So that's imparting 50 tons of load forward and 50 tons of load laterally in a truck tray, a heap of material that's raised up away from the structure that's supporting it. So we put those things in there. We made a model of the ore body that was in there, which basically allowed it to have a high compression load but not have much tension. It wasn't actually modelling the individual rocks of material, but it was able to simulate how the loads would be transferred and how the structure was moving or flexing. And under those loading conditions, we basically found that this beam that came around the front was getting really smashed. Like the stresses were really bad. So the first thing we thought to do was basically go in there and beef that up. And so it was an I-beam sort of section which had some end plates on it to try and see if it was moving. That made it worse. We then put like backing plates on it so it would be thicker. We stepped the thickness so it would go from sort of thin beam that was across the front wall to like a 5-to-1 ratio in change in the beam structure. Thicker beams, that made it worse. It's like, what's going on? And working with a very experienced client who has done all this sort of stuff for years and years and years, what we basically found was that because the spider structure was a global system and the truck tray was kind of down on this angle, I think it was 10 or 12 degrees, with the front wall like this, all the material wanted to fall forward, especially under that braking load and the sideways load. So the beams, the 8 beams or 4 beams that were holding the structure were basically flexing forward and they were flexing to the side. So what was happening is that beam at the front is actually getting forced forwards, and the beams at the back were basically not resisting it. So whatever we did at the front, we would continue to get that break, that stress raiser. And yeah, so what we ended up having to do was we ended up having to increase the torsional stiffness of this rear beam so that it wouldn't roll over as much, and the vertical stiffness. We had sort of like one big beam that came back to the main pivots and then 3 smaller beams. The change at the back of the tray resolved the issue at the front of the tray, and we could make it more lightweight again, and we could get rid of all this technicalities with different step beam sizes and having to cut certain changes into the beam and things like that. So that was a real heavy learning for me on the job. And I think not from then on, but we will always then look at the structure as a whole structure, or as big a structure as we possibly can, but we need quick wins. We want to fail fast. We want to understand what this thing's going through. So in regards to FEA, finite element analysis, you basically run as coarse a mesh as you possibly can to be able to simulate the portion of structure that you think is going to be involved in the movement and the stress of the system. And then from there, run as quickly as you can, run a simulation, figure out where those hotspots are, and then refine.
Yeah.
And I think, there's new tools now, obviously, to be able to do that better and much faster than what I was doing it back in the day. But the fundamentals are still there.
Yeah, the same thing applies. That's always what we aim for. So, as you said, like in terms of like new tools, so this is kind of not far different. This massive framework here, which just mounts to a boom arm, and it's got a tool inside it. This thing can tilt forwards, back, sideways, whatever it's traversing.
So this is a robotic truck that has an autonomous, or it's an autonomous robotic truck which has an arm that gets deployed to hold a very expensive tool.
So downhole assay tool.
Yeah, and it basically has to be stowed and then move across a very bumpy, lumpy ground under its own weight, and then basically be deployed into the free air, spot the hole, drop down.
Start, stop, while going over.
Yeah, and it's also hanging out in the air while it's starting to go to the next one.
Exactly.
That's a pretty big load.
Exactly. So there's many load cases, either 15 or 20, that between us and Epiroc, who's the client, we I guess agreed on. That's what the use case was going to be. You could easily go too conservative and have a box that's massively overweight, over designed, which is going to cause all these issues of their own. Your cylinders are then not rated to take the load, so it's working out what
compromise.
What data do you have? What can we get? Do we need to get some more data? So there was a lot of talk around that to kind of get a good middle ground. So in this case here, we came up with some concepts. We kind of knew what the size or footprint was of the actual box, the tool that had to sit within it. We started off with a simplified model. In this case, it was beam elements.
So these ones here are actually beam elements, not
correct, 3D.
Not 3D elements,
So instead of having to spend that extra effort, which is quite huge when you're trying to deal with models of this size, in terms of setup, but also like runtime, can we then set up some beams which can be parametrically driven or changed with their cross section to work out roughly what sizes do we need to limit deflection and stresses, things like that, and get a structure that does the job. From there, we then moved to a more detailed 3D model, looking at various aspects.
Oh, you got some fatigue life stuff in there.
Yeah, so this one here was fatigue. So fatigue is obviously another big one that needs to be looked at. Obviously, your limits change massively, especially in terms of welds and also bolts as well. We were basically limited to the feed holder that we were given for that truck. Things have changed a few times along the way, and we've kind of worked out that we decided that actually we can modify that now. There's kind of a joint project in a way, because we're not in charge of anything
from the feed.
So that's an Epiroc thing. So it's kind of us working with them to understand. They need to understand what our sims tell us in terms of forces, things like that. Then they need to put that back into their end. So this is not the latest version. They're actually working on the updated version right now. But they will be modifying this to basically increase the width between your lines of your bolts, so we can get some more resistance to that eccentric loading that we're seeing, and also further up and down. So basically just increase the bolts and the upright corners and the lower getting hammered basically.
Yep.
But again, so this is a case where if you were to run a simplified model with maybe some rigid bodies, for example, the load share between your bolts is massively different to when you run it as a deformable. And that not only goes for the brackets, but this goes for the feed holder as well.
Yeah.
So
you're actually modelling part of the system which you can't change.
Correct.
But it has a deformation and imparts stress loads.
Yeah.
Yeah. Okay. Yeah. That's super interesting. So in the case of some cases, you'd have to reverse engineer that because you wouldn't be given that information. But we're lucky we're working with the
drawings.
OEM. Yeah. So yeah, for me, like, you know, there's a lot of stuff that I learnt around sort of structural steel simulation with this sort of stuff. Like, for instance, the deformation pattern side. Deformation patterns here on these different flanges. This is a buckling pattern. Yep. So, you know, what's going on here? Something's buckling, something's coming down, something's going up, this thing's buckling. So any flange that's hanging out in the wind like that is not going to basically resist you in compression, but you can definitely use it in tension. Lots of people out there love gussets. Gussets, in my experience, do very little unless they're specifically designed, you know, you get to know these things, especially FEA is such a wicked tool because you get to understand how things work. Even if it's simplified like this, like, you know, there's no welds and things like that, obviously it's going to be different, but you can get further and further into it and understand how things are moving. Box sections, so you can kind of see on different faces where the buckling of the plate, obviously the deformation is highly exaggerated. The buckling of the plate is going to be shown somewhere, and that'll give you an indication of the way the thing's moving. You can obviously exaggerate the deformation to kind of figure out what's going on. Another part that comes into it as well is design for manufacture. So when you're manufacturing this thing, how are you going to weld it? Where are you going to weld it? How flat is it going to be compared to what your modelling is? Bringing that on the ground feedback back into the setup of an FEA model, having the outputs of these simulations and showing the client, and the client goes, actually, we've had a crack there. Yeah, we've had a crack there, or we've seen this thing in the past. You really got to leverage what the person on the ground has seen, especially in regards to inputs and then in regards to sort of the outputs and validating the outputs. Even calibrating, you've got to calibrate the outputs sometimes because this thing is not 100% accurate. It's as close to accurate as we possibly can get, but calibration will always get you closer than not having a calibration.
Yeah, exactly. Yeah, so this one here is actually a classic case of that. So this is basically an off-the-shelf power finger that's been modified. This is a model that's been cut, but essentially it's got this downhole SA tool mounted to the end of it.
Yeah, well, it's like a couple of meters away.
Which is, so it's massively hanging out. We're responsible initially for the design of the front portion, the actual tool spine and the knuckles with all the pulleys and stuff that are involved in sending the connector to the tool to send it down. We initially didn't really have any involvement in this power finger or modified power finger portion.
The client sent it to site?
They sent it to site and essentially they had cracking occur through here, and the bottom two corners. And also in this lower portion, so I think this is a simplified one where we've just not modelled the weld, but it still highlights the same. You know, the force is still going through a portion which has been segmented and bonded to the back. Anyway, there was cracking here also through the weld that's there.
So it's kind of validating what you've seen on the site. And this is a classic case of, we wish our clients came to us earlier.
And that's what they all say. That's what they all say.
And they always say, we've spent this money getting this thing done by someone else who didn't check it. We've only got a certain amount of money left. Please help us. So that's our aim for this year, is to help more people before they spend money. But this is a classic example of just, you know, having to pick up what someone else has done or what's been designed. Because a lot of time people think, oh, that's going to be fine. It's designed for this thing.
It'll be right.
Should be right. You know, that sort of thing. But in any case, we went and did it, and we've simulated it. We've calibrated it with what we've seen in the field. What did you do afterwards to sort of improve it? You just kind of looked at the loads and
so we went through a number of iterations.
So this is adding extra plates to the OEM piece.
Correct.
Yeah. So to make a fit for purpose
So
design.
I think with the structure of this, one of the things to look out for, or a major red flag, is when you have parts doing a lot of load and you have a sudden change in geometry or drop in stiffness, which is the case here. It's a very combined load. The way this thing is moving is what we've found. So being able to brace that completely all the way through and basically tie it together to this base eliminated the issue. So unfortunately, in this case here, it was too late, and yes, it would have been nice if we were involved sooner. And it was a hindsight, I wish we had done that before kind of scenario.
But it's all too common. It's a bit unfortunate. We're sharing this because we want to help more people, but we see a lot of people go and use these tools in the way that they're uneducated in the way that they should be using it. And we've actually seen some that have been pretty bad, like things that are safety critical or suspended loads with people who are around them. They do the simulation of this structure in a lot of the time it's SOLIDWORKS simulation because it's easily accessible to one of your middle range packages for SOLIDWORKS. They put the wrong boundary conditions on it, and then the thing in FEA looks good. They go and make one, and all of a sudden it's bending more, or it's broken, or it's got a crack, early onset cracking, or whatever it is. And then they come to us and go, but the FEA looked great. And probably what you said before, probably every 2 years, maybe once every 2 years, we get someone who's spent a load of money, and they come to us with an engineering report of what was done previously, and some photos and videos, and even a product that's broken, and go like, how do we get in this mess? And within the first 3 pages of these engineering reports, we can tell.
They're pretty much doomed from the start. Like, so as unfortunate as it is, it's just a fundamental out scenario.
But having said that, if someone capable and skilled in the art of FEA, because it is a specific science, and it is a specific tool that needs to be educated to be used. Having someone look over that set up from the start, and then having someone else go and do it. Like we would love to be able to educate more people on how to use it. If you want us to do it, happy to do it. By all means, it's our bread and butter. But even if we were to come in a consulting way and teach people how to use the tools, we're very open to that. And we're doing that with our electronics things these days. We've got Alan with 30 years of experience with RF, helping startups to sort of understand their RF pathways and stuff, not particularly doing the design for them, but just giving them some high-level information. Same thing as us with FEA, we can do the same thing. At the end of the day, we just want to see more people put out more awesome things to the market, creating new value to the businesses that to the systems that they're creating, and do things right from the start. So we've done some other stuff as well with FEA. We've done quite a lot of plastics design. For injection molding, we've done lots of different structural steel, billet aluminium. This is a billet aluminium.
Yes, this is another one where a client came to us with a sea container door brace to address safety issues, slamming doors on windy ports when they've got one of these open and they're loading it. They came to us with a proposed concept that they had put together. We had a model, actually, a machined part that had been done. Initial proposed design was basically made out of steel.
The customer had already engaged a very good client of ours also who does castings. And then they referred them to us. We worked with them before on a number of different castings. So this product is basically going to be die cast, aluminium, high pressure or low pressure die cast.
Correct.
And so we had to basically simulate it for that particular manufacturing process, but we could then emulate it, virtually simulate it, and then we could basically CNC machine a version which would be very close, using 6061, which would emulate closely to a die cast material.
So we worked closely with the client again to understand exactly how it was going to be used, with what containers was it going to be used, are there any variations with the containers, lock that in, understand and be sure that...
That's a process in itself,
important,
right?
Exactly,
so
before you even start.
You're looking across the whole product life cycle and the range, or the bell curve, so to speak, of different applications. And when talking with customers, try to figure out as quickly as possible where the product is going into. So you can have your one pet use case, so to speak, or your most commonly used use case, which might be sold to a specific customer or specific domain. But if there is a range, you've got to know what that range is, and you've got to know what the distribution of that is.
And the variance in the things that, so in this case here, like there are variances geometrically. In terms of the door, so getting the fit, you've got to account for what that might be. Test it. We machined a prototype or two. I think we even printed some to begin with. Get a feel for the handle. How does it feel? How does it fit? And then it obviously comes down in the end. No matter what you do, it's got to be manufacturable. So I think in this case here, we knew that it was going to be cast. It was understanding draft angles. making sure that they were a part of the design in the end, and that it was modelled in that way.
And the prototype was actually manufactured with those draft angles and things like that on it as well. There's a lot of detail here.
So it's, again, this is something that many people would probably oversimplify things. I think for a little bit of extra effort in this case, because of, we're pretty good with the tools, I guess.
Yeah, but the effort has always paid off. We've never had anything come back that hasn't passed in FEA, passed in some sort of physical testing, and operated in the field. And that's the major advantages of using FEA properly, is that you can do virtual simulation, virtual prototyping.
Yeah.
So you can basically go from design all the way through to a pre-production or production grade design, which will most likely 99.something%, even more. We can guarantee it as long as we have the correct safety factors and we've done all of our due diligence in inputs and outputs. You may not even have to make a prototype. You may be able to go directly to production.
Yeah, exactly. If you can get your operational use cases and you understand them well enough, you can pretty much guarantee it every time.
Yeah. So the flex floor lightweight truck tray that I did a whole bunch of work on back in, I think it was 2012, something like that. I remember we did 15 big iteration changes. We had one in simulation. We had one prototype that went out to a mine site. That prototype worked for 4,000 hours, had no issues. Got decommissioned and assessed. Absolutely no cracks or anything like that. That's the ideal use case, because the manufacturing of one prototype could far exceed the cost of the FEAs by double, triple, 5, 10 times, you know what I mean? Depending on the complexity of the prototype itself. So you want to do as many iterations as you possibly can in simulation. Digital twins, that's all those sorts of things these days. As many virtual simulations as you can, getting as close to the reality as you can, and understanding what the variances are. So if there is any unknowns or any variances that we can't check, then we go to a prototype.
Yeah. So it's basically making sure that, allows you to do things that are probably not feasible otherwise from a cost point of view. Feasible.
Well, you can't make 15 truck trays.
No, exactly.
The first truck tray, if we made that first truck tray, it would have been a spectacular failure. And that probably would have been the death of the project. You know what I mean? So that's probably the same with a lot of these things as well.
Yeah, exactly.
So, FEA is an amazing tool. Same with CFD, same with all these computational simulation tools, but they have to be used right.
Yeah, exactly.
Have to be used right.
Exactly.
Oh, DEM. This is one we did back in the day. This is a new one.
This was the simulation, I think it was on the MT6020. This shows the coupled simulations that you can do.
It's pretty awesome. So this is putting in discrete elements with a different distribution of size, and then basically tipping them off. And then the bottom simulation is taking the input loads from those simulated rocks and looking at the point loading that's being imparted on the structure. So this was a lightweight truck tray we did for underground, which was very specific to a mine site which needed a certain volume, like a larger volume than they currently wanted. So we had to come up with a specific design which was specific to the manufacturing processes for this particular client. We achieved it. It worked really well. We had one failure, which was the hang up on the back, which we needed to put a plate into the back because the angles weren't correct. So it was an oversight on the angle, but we still achieved the brief of getting the amount of ore volume in there.
But again, now that's something that, with this new technology, that is something that we could address again without even getting to the point of building the thing.
So this thing is actually taking the loads from those rocks, imparting it on the structure. The structure is a proper full FEA using welds and everything like that, and looking at the point loading that's being applied. And then we can use that as an input or understand what the inputs are. So I think it's that there's a point within this simulation where it's sort of tipped and it's moving.
It's that impact initially, right? That loads this thing up, and then that at any point throughout this dynamic or explicit simulation, you can pull the impact loads at that point, impart it on your static stress analysis, and pull your stress.
And one of our clients who's making crusher pieces, for want of a better word, they do the DEM in-house, and then they provide us the information, and we then do the iterative design analysis and optimization. It's actually funny there. There's a hot spot there from like bending of the truck tray. I think. Yeah, see that on there? Look at that.
Yeah.
It's pretty interesting. But anyway, yeah, these things are cool. So, you know, full virtual simulation these days where you are simulating the loads, not assuming the loads or not having to go out and test what the loads are, and then running the simulation, having it directly input the loads to the analysis. And sometimes even, you know, things may move and you can do the bidirectional coupling, which I don't think we've done.
Yeah,
you know,
but it's there.
Yeah, it's pretty awesome. But this is the new website page, check it out. One thing I wanted to point out here was, if you scroll down to the bottom, we've used data loggers a lot in the past. So this here is a plot, very crazy looking plot from one of the logging boom devices where we were looking at G-forces. And so from those G-forces, you can basically look at the peaks and the troughs. You can average it. You can do all sorts of stuff. That data logger is actually a Pelican case that we have a high-speed data logger in. We have some mil-spec connectors on the outside of it. We set it up with the power source or with the battery, and then we basically wire in these off-the-shelf sensors. Some of the sensors can be pretty expensive, you know, like $400, $500, $600. We can have different actuators as well, but mainly sensors that are coming in. And it gives us the ability to go and get real-world inputs. So the assumptions are, you know, I don't know what the saying is. If you make an assumption, you're making an ass of you and me, an ass of you and me, whatever it is. But it is the case. If you make a wrong assumption, you are effectively wrongly simulating what the system's doing, and you could have a failure from that. So the data logger is one piece. Having a virtual simulation which basically imparts global loads onto a structure, and, you know, instead of just putting a point force here or a pressure load, it's actually imparting distributed pressure or something like that. That's much better than assuming something. If you can make very good assumptions, very well educated assumptions, and you can verify them and document them and even calibrate them with something on site or from your environment, that's great. The majority of what we do is that, but you've got to spend a lot of good time and effort to understand the distribution of what your system's going to go through, figure out in your brain, or probably with hand calculations, which one is the worst. So if you've got a bell curve and the middle of the bell curve is actually not the worst case loading, you probably want to go to the worst case loading, even though maybe only 10% of the users or devices are actually going to go through that load, because invariably you don't want this thing to fail. And that's kind of the whole product development cycle, the whole product development opportunity is figuring out the balance between over-engineering something or just throwing heaps of material in it, which is kind of wasteful and expensive, or under-cooking it. And FEA is an amazing tool to be able to figure that out, but you've got to put a lot of effort into understanding what this thing goes through and how you are going to emulate the potential structures. When you do that, it's a phenomenal tool. My work and Dan's work these days is actually working with the client to understand the conditions and what they're trying to do with the product, and sometimes telling the customer, don't do the engineering. Go and do, you know, understand your market, understand your product market fit, understand the inputs and outputs, boundary conditions, understand what you've got already from understanding of what is happening in the field, and then we come up with a design which is fit for purpose and an analysis or an engineering program that fits what the requirements are. And too many people in our recent, you know, and long-term experience are kind of spending money on engineering too early. Part of the engineering is actually doing that work, but a lot of the time it's, you know, you don't have to do engineering to go and figure out what this thing's going to go through. That needs to be down to the guys on the ground who are actually doing the hands-on hard yards and seeing what this thing's interacting with. Your end user, you've got to understand your end user. Don't do the engineering if you absolutely have to do it. Get some experienced eyes across it for your design concepts and your engineering process, and then make sure the people that are doing the work are skilled enough or have enough guidance to do that.
All it takes is getting it wrong at that very start, and everything afterwards is just a waste of time.
Out. Unfortunately, but when it's done right, it's amazing. So we would love to see more people harnessing these tools, making awesome products from the very start, doing less physical prototyping. Physical prototyping is amazing, but you can do a lot more in virtual prototyping. Let's go and make cool. Let's go and make cool products.
I just love coming in and fixing stuff.
fixing other people's problems. It is pretty cool. It's also heartbreaking.
I think we all get a kick out of, like, I mean, that's why we do it. There's nothing more satisfying than doing something hard
We've got 2 clients right at the moment where they've spent a whole heap of money developing something, and Dan and I have had to tell them we have to throw it in the bin, unfortunately. And unfortunately, that thing's not going to work, and here's the reasons why, and we can validate it in FEA. We can go and do this thing, which we have quantifiable understanding of how to do that, and we go and make it, and we do it from scratch, and it works. It will work. These are 2 new clients, but we've done it before. We've had situations where people have spent hundreds of thousands of dollars, if not more, with other providers who, and really unfortunately, this is totally unfortunate, junior guys coming out of university who are unguided. You know what I mean? Like engineering, yes, it's a skill, you can get it from university, but there's more to it. You know, that's why there's graduate programs and things like that. Our guys in the office go through a regimented discovery and design process. We have a FEA Bible, but you need to understand how to use these tools, because if you f it up, you're throwing away a lot of money, and not only money, time.
Yeah.
Time is the big killer in a lot of these things.
There's a number of softwares out there. I think, again, ANSYS is obviously it's a kind of tried and tested one. Having, you know, obviously there's things like SolidWorks simulation, but I mean, we've compared the two side by side a number of times. People don't
like it when we when we do that. We've been told before, do not do this. You're not allowed to compare them 2 by 2. But you know, they have their uses. If you've got SolidWorks simulation, it's a great tool if you use it right. Yeah. You can get some insights.
Some fast outputs.
Yeah.
If you,
we just jump to ANSYS because we know it's tried and tested, like you said, and as long as you use it right, the outputs are very spot on. So we love it, and we do really want to see people successful. We get a kick, especially Dan, out of fixing people's problems. But if you can come to us earlier, wow, that would be amazing. We don't want to see anyone waste any more money. It's just, it's heartbreaking, absolutely heartbreaking. Even if we can just help with a 15-minute Teams conversation as to giving you some guidance, then let us know. Let's go and do some cool.